Page 86, question number 37. Like a lot of problems, try to draw a diagram. I'm going to pause this and draw the diagram. This problem takes place in two phases. You're driving along, you see a traffic light turn yellow, going to red. During phase 1, you'll be traveling a distance of d sub 1. That's when you're still traveling a constant velocity v sub I, unknown right now. But you have not yet put your foot on the brake pedal, but you're moving your foot from the gas pedal to the brake pedal, and we're assuming uniform velocity during that phase, so there'll be one equation with basically three quantities. You have your v, your s, and your t, and they're related by the equation v equals s over t. Your v in phase 1 is v sub I, constant velocity, initial velocity, staying with that velocity. I'm calling my s, I'm going to call that d1, and I should have probably called it d sub 1, but I mean s sub 1, but it doesn't really matter, d sub 1. And t, it tells you, is 0.6 seconds is your reaction time. It's how long it takes to get your foot on the brake pedal. In phase 2, you'll be decelerating, and we usually have 5 quantities: v sub I, v sub f, a, s, and t. Well, v sub I is literally v sub I. You're going to be coming to a stop, 0. Your acceleration, it says, is negative 6.9 meters per second squared. S, we're calling that d sub 2. And then t, I don't know, it doesn't really matter right now. I could just call that t, but I won't need t sub 2. Excuse me. Alright, so we want an expression for the smallest distance, s sub s, from the corner in which you could stop. Well, s sub s will be equal to the sum of d sub 1 plus d sub 2. Once again, those are all distances. If you're going in a straight line, they're displacements. Well, in phase 1, if I go back over there, in phase 1, switch to a different color, there's one equation. The generic equation is v equals s over t, or d over t. But with the specific labels for this particular problem, it's v sub I equals d sub 1 over 0.6 seconds. I'm going to leave the units off for now. Well, in other words, d sub 1 equals 0.6 v sub I. Alright, so in phase 2, we have our 4 uniform acceleration equations, of which the fourth one is very useful. In generic terms, we have v sub f squared equals v sub I squared plus 2as. So if we plug in the particulars for this problem, v sub f is 0, v sub I we're still using as v sub I squared, plus 2 times the negative 6.9, and I'm calling s, I'm calling that d2, d sub 2. Alright, so my stopping distance in equation form will be d sub 1 plus d sub 2. Actually, I need to solve this equation I just wrote down there, the 0 equals v sub I squared. But if I rearrange that and solve for d sub 2 will be, well, I move the v sub I squared over to one side, I get a negative, but I'm going to be dividing by another negative eventually, so the negative will cancel out. But to make a long story short, I believe I will have, when all is said and done, v sub I squared divided by 13.8. I haven't put that in decimal form yet, because 2 times 6.9 is 13.8. Yeah, I believe that's correct. And I'm going to put that in decimal form. D sub 2 equals 0.072 v sub I squared. So the expression, or the equation, for s sub s the expression is the right-hand side of this, is d sub 1 plus d sub 2. In other words, 0.6 v sub I plus 0.072 v sub I squared. So the right-hand side of that is the expression for your stopping distance in terms of v sub I. And then for part B, where it says if your initial speed is 35 kilometers per hour, I would convert that into meters per second. I won't do that right now. Convert that to meters per second, and then plug it into that equation that I have at the bottom to get your velocity, your stopping distance for any given initial velocity, because everything that I did at the bottom here is in terms of meters, and standard units, meters and seconds, not kilometers and hours. So that's problem 37.